So today we're looking at the lower central series of a free group. And we have two theorems to prove. We're going to list them one after another right away here, just to start things off. First theorem, suppose in our ring K, the action of n on 1 equaling 0 implies, n times 1 is 0 implies that n equals 0 for every integer n. Then we let R be a mapping of our generating set into its associated Magnus algebra. I forgot what it was called there for a minute. Just Magnus algebra such that our old omega of R of x is at least 2 for all x and x. Oops. And let G be the homomorphism of the free group into the Magnus group of x. Homomorphism such that G of x is 1 plus x plus R of x for x and x, as we recall. For all n at least 1, we have that Cn, the nth lower central series of the free group on x, is the inverse image under G is under G the inverse image of the subgroup 1 plus a hat n x with 1 plus the nth Magnus thing of x as a subgroup of lambda x. And there's another theorem which states for all x and x, for all x and x, let Cx be the image of x in the quotient in fx divided by its own derived group, if that is a thing. Let G be the graded integer algebra of the filtration of the lower central series of the free group of x, which is a filtration, of course, of the free group of x. The unique homomorphism of the free integer group, free integer algebra, the free Lie integer algebra of x into G, which extends C, is an isomorphism. So loosely speaking, the graded Lie Z algebra associated with the free group of f of x is the free Lie Z algebra Lz of x. So we are going to do a bit of notation swapping here. F as f of x and so for the Magnus group, the Magnus algebra on the integers, and we write Cn as the nth lower central series of the free Lie algebra on F. Gamma n be 1 plus a hat n of x. And we are going to let alpha from these free Lie Z algebra on X to our group, to our algebra, be the homomorphism described above. That is the unique one extending C, extending the image of X in f of X over its derived group. Now, let's look at the proof here. Part A is preliminary reductions. Preliminary reductions. Let gamma be the homomorphism of the free Lie group to the gamma as gamma of x is 1 plus x for all x in x. Then there exists an automorphism sigma of the algebra a hat compatible with the filtration on a hat, and such that sigma of 1 plus x is g of x for all x in x. So sigma of gamma n is just gamma n for all n. As the homomorphisms g and gamma composed with sigma composed with gamma of f into gamma are equal, coincide on the generating x, they are equal, so G inverse of gamma n is just going to be gamma inverse of gamma n. We can identify by hypothesis the integers with a subring of k so our Magnus algebra for the integers is identified with a subring of our original Magnus algebra and the filtration of the integer Magnus algebra is induced by that of the original Magnus algebra. As gamma maps f into our integer Magnus algebra, we only need to show our theorems under our base ring being the integers, r being 0, and g being equal to gamma. Alright, next up, we're going to show part B is the surjectivity of alpha, as x generates the group of f, which is its own first central series, the image of x under C generates the integer module G1 as the first central series or the second central series, which itself generates G as a Lee's integer algebra, so C of x generates G, so alpha is surjective. Part C is not titled, alright. We identify the graded algebra of the Magnus algebra, the grade of the Magnus algebra with the free associative algebra of X under canonical isomorphisms, nth grade of A of X going to A hat n over A hat n plus 1. We then write for all n greater than 1 being an integer, being at least one integer, being a positive integer, we write that f of n, f to the n, f super n is the inverse image under gamma of our gamma n. And we know that f to the n is an integral central filtration on f, of course. Now we're going to let g prime be the associated graded Lie Z algebra. Then we're going to let f be the Lie algebra homomorphism of g prime into ax, the Lie algebra homomorphism associated with gamma. Now our lower central series inside of our f to the n for all n at least 1. Hence, we have a canonical homomorphism epsilon of g as the direct sum of our c to the n over c to the n plus 1 into g prime as our sum of f to the n over f to the n plus 1. With the following diagram, which we're going to need a new page for. And it looks like we have our integrally algebra on x, free mapping under alpha to g, mapping under eta to g prime, mapping under f to the free associative algebra on x. I'm going to write beta as the composition of these two last steps, which is explicitly if u is the class of an integer of an element w and Cn modulo c to the n plus 1, the n plus 1 central series, and then gamma w minus 1 is order of at least n in a hat, and beta u is the homogeneous component of gamma w minus 1 of degree n. With beta of c of x being x for all x in x. Finally, we have part D, which is the proof of our theorems. The Lie algebra homomorphism of beta composed with alpha, so going through that entire path up there from the integerally free Lie algebra on x to the free associative algebra on x, restricted to x is the identity. Hence, this homomorphism is the canonical injection. Thus, alpha is injective, and as we've already proven, it's surjective. I want to use the word thus. Bijective. Giving the second theorem. As I pointed out before, beta composed with alpha is our full map of f composed with epsilon composed with alpha, which is injective, and alpha is bijective. That means our epsilon is injective for all n at least 1. The map epsilon n of c to the n over c to the n plus 1 into f to the n over f to the n plus 1 is injective Hence, the intersection of the nth lower central series with our f to the n plus 1 gives our c to the n plus 1. We also have that c to the 1 is f, which is f to the 1. So by induction, if c to the n equals f to the n, then we have, because I need a new line, that the intersection of c to the n with f to the n plus 1 is our just f to the n plus 1. So c to the n plus 1 is our f to the n plus 1, which is our first theorem. This comes with a corollary, which states that the intersection of all of our central series, lower central series on the free group on X, is just the identity. Alright, the proof by first theorem with k being the integers and r being 0, we get that the intersection of our c to the n, the central series of the free algebra on X, is the intersection of the G inverses, of course, of our 1 plus a hat n of X, nth grade of our Magnus algebra, which is the G inverse of the intersections of 1 plus the nth grade of the Magnus algebra on X, which is, of course, G inverse of the unit, which is the identity. Alrighty. And so this comes with a remark. Let H be a Hall set, be a p-Hall set, remember those, relative to X. Let M be the magma on Fx with the map sending x and y as a pair to x and y as a commutator, which is, of course, x inverse y inverse x y. And we let phi be the homomorphism of m of x into our magma, free magma into our given magma, such that the restriction of phi to x is the identity. The elements of this homomorphism of our Hall set are called the basic commutators of the free group of X. For every integer, at least one. Let, I don't know why I capitalize that, let Hn be the subset of h be the elements of length n, and we know the canonical mapping of hn into the integer Lie algebra of x is a basis I'm guessing the image of this is a basis of the abelian group of the nth grade of the free integer Lie algebra on x. Moreover, each phi of hn is also within the nth lower central series of our x. So for all m in the hn, an n-long element of the Hall set, let phi n of m denote the class of phi of m modulo the n plus 1th central series. We see from our second theorem that phi n is a bijection of the nth Hall set and the Hall set of n words onto a basis of the abelian group c to the n over c to the n plus 1. Thus, for all w in Rf of x and I at least 1, there exists a unique alpha I in the integers indexed by as a vector of integers indexed by hi, such that for n at least 1, w is the product of I from 1 to n and of all m in our Hall set of length I, phi to the m times alpha sub I of m modulo c to the n plus 1 with the ordering done in the order as given by the Hall set, of course. Let's look at an example of this. Let's actually compute one. Let x be the set of an indeterminate x and y with, of course, our Hall set of length 1 being our individual x and y, our Hall set of 2 being x, y, and that's exhaustive, I believe. Then every element w in f of x can be written as w congruent to x to the a, y to the b, the commutator of x and y to the c, modulo to the third central series with a, b, and c integers. for w being xy to the n, a and b being n, and c being n, 1 minus n over 2, we get xy to the n is congruent to the x to the n, y to the n, xy to the n1 minus n over 2 modulo C3. And there's one last chapter in this section before we move on to the Hausdorff series, so let's just finish off with that. This is p-filtrations of free groups. So we let p be prime, and k being, I believe this is the finite field with p elements. And gamma be a map from F, the free group of X, into our Magnus algebra of X, a homomorphism. It's gamma of X equals 1 plus X for all X in X. And finally, we write on a new page f sub n p of x to be gamma inverse of 1 plus a hat of n of x. Then the sequence of our fpn of x along n, of course, is an integral filtration, central filtration, of course, on f of x, which is also separated as gamma is injective. It is called the p-filtration on f of x. Proposition: suppose that x is finite. For every integer n being at least 1, the free group on x modulo divided by the nth of this p-filtration of x is a finite p group of no potency class, so like the order to which the series bottoms out, of at most n. Alright. And the proof: by induction on n, we show that fnp x over the next p-filtration of x is a finite commutative p group for all n at least 1. Then for all omega in Fn p of x are gamma w minus 1 inside of alpha of the Magnus group, Magnus algebra on X, is order at most n. We write as delta n of w the homogeneous component of gamma w minus 1 of degree n. Then the mapping delta n from the nth p filtration of x to the nth grade nth filter of the free associative algebra on X is a homomorphism with kernel of our fp n minus 1 p filtration of f. So they're modding out the quotient, modding out the kernel, that is. Quotienting the kernel, I kind of mixed them all up. Is isomorphic to the image of delta n to a subgroup of an. Since x is finite, a to the n of x is a finite dimensional vector space over our finite field of p elements, and hence a finite commutative p group and so is the quotient of the nth p filtration of x over the n plus 1th p filtration of x. There's one more proof and a corollary, and we'll call it one more proposition and a corollary, and then we are done. For all w not 1 in fx, there exists a finite p group G and a homomorphism f of x into G such that f of w is not 1. In the proof, there exists elements x1 through xr in x and integers n1 through r in integers such that w is the product of each xi into the I. Let y be the set of x1 through xr, the canonical injection of y into x extends to a homomorphism alpha of the free group of y into the free group of x. Now we're going to let beta be the homomorphism of x of the free group of x into the free group of y. such that the restriction of beta to y is the identity on y, and maps the elements in x not in y to 1. Then beta is a left inverse of alpha on y. That's why it generates f of y. Beta composed with alpha is the identity automorphism of f of y. There obviously exists an element w prime in f of y such that w is the image under alpha of w prime. Then beta w is w prime and not 1. Now the intersection of the p-filters of f on y, not x, is 1. So there exists an integer n at least 1 such that beta of w is not within the nth filtration of y. By our first proposition, the group G of f of y over the nth filter of y of f of y is a finite p group if f is the composition of our beta and the canonical homomorphism of f of y onto g, then f of w cannot be 1. And this comes with an immediate corollary, which states that the intersection of the normal subgroups of finite index in f of x is just the identity. And that's everything for our discussion on Magnus algebras. Up next, we're going to be talking about the Hausdorff series, which is probably going to be a few days, but after that we are done everything from Bourbaki, and then we'll be finishing, I believe we'll be finishing the book of Humphreys, and then we'll be discussing groups, and I don't know how that's going to go at all, but we'll get there when we get there, right? I think we're making good progress. Yeah, thanks for watching.